Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the IGCSE chemistry topics. This is covalent bonding. I'll begin with the simple terminologies. Covalent bonding is formed between two or more non-metal atoms, and these occur by sharing electrons. When they ask you to define a covalent bond, this is the electrostatic attraction between the nuclei of atoms and a pair of shared electrons between them. Remember, these electrons are negatively charged, and the nuclei, due to the protons, is going to be positively charged, so the attraction between the two is going to be the covalent bond. For example, here we see one atom with a positive nucleus and another atom with a positive nucleus. They are sharing a pair of electrons that is negative or that are negative, and the attraction between the negative electrons and the positive nuclei is going to be the covalent bond. This is a common question that could be 3 marks, defining a covalent bond. Next, we look at examples of covalent bonds. For example, between a hydrogen molecule, we know one hydrogen atom and another hydrogen atom. Each has one electron in the outer shell, so they will share the 2 electrons, creating a structure that looks like that. And here I put a reminder, remember this is not helium, it's just 2 hydrogens coming together. The number of protons in the nucleus is still not changed, so it's still hydrogen atoms, but they are sharing electrons. We do not combine them to create a new superatom, which will be helium. That is not the case. The ability of 2 hydrogen atoms to come together and form a molecule is because when a bond is formed, energy is going to be released because this is going to be an exothermic process. The process of bond formation is exothermic, making them stable, and that is why we see it's going to be preferred or it's going to be favored in that direction. Other examples we see here nitrogen. Nitrogen is a diatomic molecule made of 2 nitrogen atoms. The first nitrogen atom has 2 electrons inside, and it has 5 electrons in the outer shell. We can see those are the properties we see for both, 2 electrons in the inner shell and 5 electrons on the outside. When they share electrons, they share 3 pairs of electrons between them, making 6 electrons, and the other 2 from each atom, making the outer shell to have a total of 8 electrons after the 2 hydrogens combine together to form a triple bond. The next example is hydrogen chloride. Remember, hydrogen has 1 electron in the outer shell, but chlorine has 7. So when they bond together in the covalent bond, they share 1 pair of electrons. In the end, hydrogen appears to have 2 and chlorine appears to have 8. They have obtained a stable state. The next example we have is ammonia. In ammonia, the nitrogen has 5 electrons in the outer shell. We can see those, that, and those 2. And it's bonded to 3 hydrogens, whereby each hydrogen has only 1 electron in the outer shell. So those electrons are going to be shared, creating 8 electrons around the nitrogen and 2 electrons around each hydrogen. In water, we have 1 oxygen and 2 hydrogens. Each oxygen has 6 electrons in the outer shell. We can see those. And each hydrogen has 1, so they do share. Here we can see those 2 shared, these 2 shared, and then the remaining 4. So there appears to be 8 electrons around the oxygen and 2 electrons around the hydrogens. The other example is methane. Methane contains 1 carbon and 4 hydrogens. Still, we can see the 4 covalent bonds that are formed. Here, hydrogen appears to have 2 around it, hydrogen 2. There are 2 here and there are 2 here, while there appears to be 8 electrons in the outer shell of carbon after the covalent bond is formed. So the carbon appears to have a noble gas configuration. Next, we go to ethane, whereby we have a carbon surrounded by 3 hydrogens on one side and another carbon surrounded by 3 hydrogens on the other side. In each carbon-hydrogen bond, the carbon donates 1 electron and the hydrogen donates 1. Also, in the carbon-carbon bond, the same situation exists. So we see a total of 8 electrons around the external shell of each carbon, while we see 2 electrons around the external shell of each hydrogen. With oxygen, since each oxygen has 6 electrons in the outer shell, they're going to share 2 pairs so that they all have noble gas configuration with 8 electrons in the outer shell after the covalent bond is formed. So we have already seen the nitrogen-nitrogen triple bond. We can go to the next one, which is carbon dioxide. And again, this one has moved a bit, but you can see 2 pairs of electrons are going to be shared between the carbon and oxygen, meaning that is going to be a double bond. And 2 pairs of electrons are shared here, meaning that is also a double bond. So the structure of carbon dioxide is going to be like that. there exists 2 carbon-oxygen double bonds, and for ethane, we see a double bond here, as well as 4 other single bonds around the carbons. Now, everything we've seen so far follows the octet rule, but there are molecules that do not follow the octet rule. For example, boron trifluoride, whereby after bonding between boron and fluorine, here we see 3 fluorines, the electrons around the boron are not exactly 8. We can see 1, 2, 3, 4, 5, 6, but this molecule is going to be existing. We also see in sulfur dioxide, here there are 2 oxygens and 1 sulfur. Each sulfur already has 6 electrons in the outer shell, but due to the bonding between sulfur and oxygen, we see the number of electrons increases. This is going to be 10 electrons around the sulfur, and that is going to be more than the 8 that are set by the octet rule. So this is going to be different from the others that follow the octet rule. For phosphorus pentachloride, it's going to be a phosphorus in the center. In each covalent bond, we're going to see a pair of electrons, meaning in the outer shell of phosphorus, now we have 10 electrons, and that does not follow the octet rule. And if you go to study chemistry at higher levels, there'll be some more that can be introduced to you. Looking at the classification of covalent substances, these include simple molecular as well as giant structures or giant molecular structures. The simple molecular structures include oxygen, chlorine, bromine, ammonia, carbon dioxide, water, and the giant substances include diamond and graphite. So here we can see the structure of diamond. In diamond, each carbon atom is surrounded by 4 other carbon atoms, creating a tetrahedral structure. We can see this is continuous 1 carbon surrounded by 4 carbons, and the structure is going to be giant because there are many covalent bonds within diamond. In graphite, however, each carbon atom is surrounded by 3 other carbon atoms. For example, this carbon is surrounded by that carbon, that, and that, creating a structure that is layered. There are weak forces of attraction between the upper layer and the lower layer, and because each carbon forms only 3 covalent bonds, there are going to be electrons that are delocalized within the structure, and these are going to move within the layers with a possibility of conducting electricity. The physical properties of covalent substances include: number 1, the simple molecules have low boiling and melting points. Within the simple molecules, the forces of attraction between them are weaker, and these depend on the molecular mass. Molecules that contain a higher molecular mass are going to have higher melting and boiling points because they will have more forces of attraction between them. So for those that have lower molecular mass, the weak forces of attraction between them are going to be even weaker, and they will require less energy to be broken in order for the substance to be boiled or melted. When we go to the giant structures, these have high melting and boiling points, and this is because to melt them we need to break the covalent bonds, and those covalent bonds are stronger and they are many because the structure is giant. So a lot of energy is required to break or weaken some of those bonds in order to melt or to boil, so a higher boiling point is going to be observed. Usually, covalent substances do not conduct electricity except graphite. Like we saw previously, in graphite, each carbon atom is surrounded by only 3 other carbon atoms, leaving 1 electron that is unpaired. And so the unpaired electron is going to be delocalized within the structure, although we saw graphite forms layers, so each layer is going to have a bunch of delocalized electrons that can be able to move when a potential difference is applied across the graphite structure. The next is these covalent structures tend to be insoluble in water, except smaller molecules like ethanol, ammonia, HCl, and so on. And among these covalent structures, diamond is very hard and can be used as a cutting tool. And this is because of the strong covalent bonds that exist between diamond due to the tetrahedral structure. So common questions from this topic will ask you about the properties of simple molecules and then the properties of giant structures like diamond and graphite. So you need to know how to explain the differences in boiling points, melting points, why diamond is hard, why graphite conducts electricity, and why graphite is soft. So this brings us to the end of this topic, which is about covalent bonding. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.